Right now, invisible cords of matter connect your galaxy to every other galaxy that has ever existed, and until recently, nobody had ever managed to see one. Astronomers call it the cosmic web, filaments of dark matter and gas holding galaxy clusters together, like knots tied along one unbroken thread stretching farther than the eye can follow. It is the largest structure ever confirmed to exist, larger than any galaxy or cluster or void, and it hid in plain sight for decades. In 2025, one of the most sensitive instruments ever built finally photographed a piece of it directly. Tonight, we follow that thread from its faint first trace to its true shape and discover what has been quietly connecting you to the rest of the universe all along. If you've enjoyed following these threads with me tonight, consider tapping like and subscribing. It truly helps this small channel to keep making this, and it costs you nothing at all. Get comfortable now, and let's get started. In 3, 2, 1, liftoff. Picture a single farmhouse window, lit up on a country road at midnight, with no other light visible for miles in any direction, front or back. That is roughly how a galaxy looks from far enough away. One glowing point, surrounded on every side by black, with nothing at all in between. For most of the history of astronomy, that is exactly how galaxies were treated, as isolated points of light adrift in an emptiness with nothing connecting them. You have probably felt this same impression yourself, looking up on a clear night, or paging through a photograph taken by a great telescope. One bright galaxy here, another bright galaxy there, and everywhere else, simply nothing at all. It feels obvious. It feels like plain common sense. And for a very long time, nobody had any real reason to think otherwise, because nobody could yet see far enough or clearly enough to know better. Even the photographs themselves seemed to confirm it. Long exposures of deep space, the kind taken patiently over many hours on a cold mountaintop, show exactly what you would expect from a universe of true islands, a scatter of soft, glowing smudges hanging in a black field, each one its own tiny galaxy, each one separated from its neighbors by what looks, to the eye, like absolute and total emptiness. No bridge, no thread, no visible connection of any kind. If you had asked any working astronomer for most of the last century what filled the space between one galaxy and the next, the honest answer would have been almost nothing worth discussing. And that answer was not a failure of imagination. It was the best answer the evidence available at the time actually allowed. Point the eyepiece at one faint smudge of light, and there it sits, alone, framed by darkness on every side. Move the telescope a few degrees, and the next smudge appears exactly the same way, its own small island, with no visible thread connecting it back to the one you just left behind. Generations of stargazers built their entire mental picture of the universe on exactly this kind of evidence, because for most of history it was the only evidence anyone had. Nothing about looking harder or longer at any single patch of sky was ever going to change that impression on its own. Something else would be required, a fundamentally different way of asking the question, before anyone could even suspect there might be more going on between one galaxy and the next than empty, silent space. It helps to remember that for most of human history, people were not even sure galaxies existed as separate objects at all. Through the telescopes of the 18th and 19th centuries, certain patches of sky showed faint, glowing smudges that astronomers simply called nebulae, a word that just meant clouds. The French astronomer Charles Messier catalogued more than 100 of these smudges in the late 1700s. mostly so that he and other comet hunters of his day would stop mistaking them for the comets they were actually searching for. A little later, the astronomer William Herschel, working with his sister Caroline and his son John, spent decades sweeping the sky with the largest telescopes of their era and catalogued thousands more. But cataloguing a smudge is not the same as understanding it. Nobody yet knew whether these smudges were clouds of gas drifting somewhere inside our own galaxy, or something else entirely, perhaps whole separate galaxies of their own, so unimaginably distant that their billions of individual stars simply blurred together into a single soft haze. This was not a small disagreement among a few stubborn professors. It went to the very question of how large the universe actually was, and whether our galaxy was the whole of it, or merely one small piece of something far larger. The disagreement came to a head in 1920, in a public exchange at the Smithsonian Institution in Washington, remembered today as the Great Debate. On one side stood the astronomer Harlow Shapley, who had recently used the positions of ancient star clusters scattered around our galaxy to correctly work out just how enormous the Milky Way truly was, and how far our own sun sat from its center. From that real and careful work, Shapley then argued that our galaxy was so large it must be, essentially, the entire universe, and that the spiral-shaped smudges seen scattered across the sky were smaller, nearby objects contained comfortably well within it. On the other side stood Heber Curtis, who pointed to something different, stellar explosions, called novae, that occasionally flared up inside these spiral smudges, always looking far fainter than the same kind of explosion looked when it occurred inside our own galaxy. If the explosions themselves were genuinely similar, Curtis reasoned, then the only way they could look so much fainter was if the spiral smudges containing them sat at truly enormous distances, making them separate galaxies in their own right, island universes lying far beyond our own. Both men were serious scientists working from real data, and both were partly right and partly wrong, and neither one had quite enough evidence that night to settle the question for good. The audience that evening left with no clear winner declared, and the two papers were later published side by side, a rare and honest acknowledgement that the argument itself mattered more than any premature verdict. A few years earlier, an astronomer named Vesto Slipher, working at Lowell Observatory on a hillside above Flagstaff, Arizona, had already spent long nights attaching a spectrograph to the observatory's telescope, splitting the faint light of these spiral smudges into its individual colors, the way a prism splits sunlight into a rainbow. Buried in those thin bands of color, he found something strange about many of these spiral smudges. Their light was shifted, stretched toward the red end of the spectrum, in a way that suggested they were rushing away from us at tremendous speed, faster than almost anything else yet measured in the sky. Nobody yet knew quite what to do with that observation, since the idea of an expanding universe had not yet been proposed, but it would turn out to be one of the most important clues in the entire story. The final answer required a bigger telescope and one very particular, very faint, blinking star. The star belonged to a class known as Cepheid variables, stars that brighten and dim on a steady, predictable rhythm and whose true brightness can be calculated directly from the length of that rhythm. Find one of these stars, time its pulse, and you can work out not just how bright it truly is, but how far away it must be for it to look as faint as it does from Earth. In 1923, using the 100-inch Hooker telescope at Mount Wilson Observatory in California, then the largest telescope in the world, the astronomer Edwin Hubble found exactly this kind of star inside the great spiral smudge in the constellation Andromeda. He timed its rhythm, calculated its true distance, and the number that came back settled the great debate almost overnight. Andromeda was not a nearby cloud of gas inside our own galaxy. It was a separate galaxy entirely, hundreds of thousands of light years further away than anyone on Shapley's side of the argument had allowed for, containing its own hundreds of billions of stars. Curtis had been right. The universe was not one galaxy. It was countless galaxies, each one its own island, scattered across a gulf of space so vast that the light reaching Hubble's telescope that year had left Andromeda long before human beings had learned to write. Hubble was not finished. Over the following several years, he and his colleagues measured distances to dozens of other galaxies the same patient way, one blinking Cepheid at a time, and then set those new distances beside Vesto Slipher's older measurements of how far each galaxy's light had been stretched toward red. A pattern emerged that neither man had fully anticipated. The more distant a galaxy was, the faster it appeared to be rushing away from us, in a clean, almost startlingly simple proportion. By 1929, Hubble had published this relationship for the world to see. It meant that the stretching of a galaxy's light was not just a curiosity. It was a genuine, usable measuring stick. Read how far the light had been stretched, and you could calculate with reasonable confidence how far away the galaxy actually sat. That single relationship would go on to matter more than almost anyone in that room could have guessed at the time, because it eventually gave astronomers the one tool they needed to escape the flattest, oldest limitation in their entire field. That limitation was depth. Once it was settled that galaxies were separate island universes, scattered across unimaginable distances, the next obvious question was how exactly they were arranged. Randomly, the way sand might scatter across a table, clustered together in some places and left empty in others. Nobody could yet say, because nobody could yet measure it properly. For decades after Hubble's discovery, astronomers did what they could with the tools available to them, which mostly meant photographing the sky, patch by patch, and cataloging every faint smudge of light bright enough to register. Great surveys were carried out this way. Most famously, the National Geographic Society and Palomar Observatory Sky Survey, carried out through much of the 1950s, using a wide-field telescope at Palomar Observatory in California. Astronomers there spent years exposing enormous glass photographic plates to the night sky, one region after another, patiently marking down the position of galaxy after galaxy after galaxy until the entire accessible sky had been documented. The result was something like a family photograph taken at a crowded reunion. You could see clearly enough who was standing where, side to side, left to right, but you had no way of telling who was standing close to the camera and who was standing much farther back, packed into the same flat rectangle of film. Every galaxy on those photographic plates was pressed onto the same two-dimensional sheet of sky, its true distance from Earth entirely hidden from view. Two galaxies that appeared to be close neighbors, practically touching in the photograph, might in truth be separated by hundreds of millions of light years, one simply sitting much closer to us than the other, along the same line of sight. The catalogues grew thicker and thicker across the 1940s, the 1950s, and the 1960s, and still nobody could say with real confidence what the universe actually looked like in three true dimensions, rather than as a flat picture pinned to a wall. The tool that finally solved this problem had been sitting in plain sight the entire time, described in outline by Hubble and Slipher decades earlier, and it worked on a principle almost embarrassingly familiar to anyone who has stood near a railroad crossing as a train rushes past. The whistle rises in pitch as the train approaches, then drops the instant it passes and pulls away down the tracks. The sound waves themselves are not changing. The train is. As it rushes toward you, each new wave of sound is emitted a little closer than the last one, bunching the waves together and raising the pitch you hear. As it speeds away, each wave is emitted a little farther off, stretching the waves out and lowering the pitch. Light behaves in much the same way. A galaxy racing away from Earth stretches its own light toward longer, redder wavelengths, exactly the way a departing train stretches its whistle toward a lower note. Astronomers call this stretching redshift, and because the universe itself is expanding, nearly every galaxy beyond our immediate neighborhood is, in this sense, a train pulling steadily away from the platform. Measure how far a galaxy's light has been stretched toward red, and you can calculate how fast it is racing away. And because Hubble and Slipher had already shown that more distant galaxies recede faster, on average, than nearby ones, that same measurement gave astronomers something Palomar's photographic plates never could: an actual estimate of distance, a third dimension, depth, finally added to a picture that had always been flat. The trouble was that measuring a single galaxy's redshift carefully, one at a time, was slow, exacting work, requiring the telescope to gather and split apart the faint light of one galaxy for many long minutes before the next one could even begin. Mapping the true shape of even a small piece of the universe meant measuring not dozens of galaxies, but thousands of them systematically, without skipping around or cutting corners. It would take a scientist patient enough and stubborn enough to attempt exactly that, at a scale nobody had seriously tried before. Her name was Margaret Geller, an astrophysicist born in 1947, working at the Harvard-Smithsonian Center for Astrophysics. Alongside her close collaborator John Huchra, an astronomer who had already spent years refining the craft of measuring galaxy redshifts efficiently, she set out in the 1980s to do something nobody had yet attempted at real scale: measure the redshift, and therefore the true distance, of every reasonably bright galaxy across a large wedge of sky, one after another, patiently, until an actual three-dimensional map finally existed in place of a flat photograph. The project became known as the Center for Astrophysics Redshift Survey, and it was carried out using a telescope at the Smithsonian's Whipple Observatory on Mount Hopkins in the mountains south of Tucson, Arizona. Fitted with a spectrograph the team built specifically to capture and measure the light of many galaxies as efficiently as they possibly could. It was not glamorous work. It was thousands of long, cold nights at the mountain, one galaxy's light stretched and measured, and then another, slowly building up a catalogue of true distances, far beyond anything a photographic plate could ever have provided on its own, eventually growing to include many thousands of galaxies, each one now finally placed at its own true depth, rather than flattened onto a single sheet of sky. In 1986, Geller and Huchra, working together with their colleague Valerie de la Parent, published the first results from a single thin wedge of that survey, a slice of sky shaped roughly like a fan, or a slice cut from a pie, stretching outward from Earth for hundreds of millions of light years. When they finally plotted every galaxy in that wedge according to its true, measured distance, rather than its flat position against the sky, nobody on the team was fully prepared for what appeared on the page in front of them. The galaxies were not scattered evenly through the surveyed volume, the way flour might be stirred evenly through a bowl of water. Instead, they clumped tightly onto thin, curving surfaces, leaving enormous, nearly empty regions in between, regions with almost no galaxies to be found at all. Looking at the printed map for the first time, One member of the team thought the pattern resembled a crude human figure, arms and legs formed out of chains of galaxies, wide empty spaces filling the gaps between the limbs, and the nickname stuck around the office for years afterward. Half a joke and half a genuinely accurate description of just how strange and organized the pattern looked on paper. This was not the random scatter anyone had expected to find. This looked deliberate. This looked unmistakably like structure. Picture a fisherman casting a wide net across the still surface of a lake at dawn. Where the cords of the net cross and knot together, they hold firm, gathered tightly into place. But look at the wide, diamond-shaped gaps between each knot, and you are looking at nothing but open water, visible clean through to the bottom. That is close to what Geller, Hucra, and de Laparent's slice of the universe actually showed once it was finally plotted out in 3 true dimensions. The galaxies gathered along thin, curving surfaces, much like the cords of that net, while enormous, nearly empty gaps sat inside each surface, much like the open water pooling between the knots. It was not remotely the pattern that cosmology had trained its practitioners to expect. Most astronomers of that era had quietly assumed that if you looked across a large enough piece of the universe, matter would spread itself out fairly evenly, the way sugar dissolves evenly through a full pot of coffee once you have stirred it long enough. Some clumping was expected, certainly, since gravity always pulls matter together to some degree, but nobody had expected such a stark, almost architectural pattern, with matter confined to thin surfaces and voids carved cleanly out in between them. 3 years later, in 1989, Geller and Hutra published a fuller analysis in the journal Science, describing what had by then become the single most striking feature anywhere in their survey: an enormous, flattened sheet of galaxies stretching clear across their entire slice of sky, so large that it ran off the edge of their map in more than one direction at once. It reached at least 500 million light-years from end to end, spanned roughly 200 million light-years across, and yet measured only a relatively thin band through its depth. A sheet of galaxies pressed almost flat compared to its enormous length and width, not unlike a single seam of rock running for hundreds of miles through solid mountain country while remaining only a few feet thick. It became known, without much need for embellishment, simply as the Great Wall, and at the moment of its discovery, it was the largest coherent structure that had ever been identified anywhere in the universe. For a great many astronomers, this was the moment the abstract idea of cosmic structure stopped being a theoretical curiosity debated at conferences and became something you could point to on an actual printed map, built from real coordinates and real measured starlight. The announcement did not settle quietly into the textbooks without a fight. Some cosmologists initially wondered whether the team had simply stumbled onto an unusual patch of sky, a fluke of the particular wedge they happened to survey, rather than anything representative of the universe as a whole. That kind of skepticism is healthy in science, and it is exactly what should happen when a single result threatens to overturn decades of quiet assumption. But the skepticism did not last. Other research groups, working with their own telescopes and their own patches of sky throughout the years that followed, kept finding the same basic arrangement wherever they looked closely enough. Galaxies clumped onto sheets and strands, wrapped around great empty bubbles, again and again in region after region of the sky that Geller and Hucra had never personally surveyed. A pattern found once might be a coincidence. A pattern found repeatedly by independent teams using independent instruments pointed at entirely different parts of the sky was something else entirely. It was a genuine feature of the universe itself. The discovery forced cosmologists to sharpen the language they used to describe what they were now seeing, because the old vocabulary of scattered stars and isolated galaxies no longer fit what the data plainly showed. Where the galaxies clustered most densely, at the crossing points of these great sheets, astronomers began calling those regions nodes, the knots in the fisherman's net. The places where entire galaxy clusters gathered in their greatest numbers, often glowing with the combined light of thousands of individual galaxies packed into a comparatively small volume of space. The narrower bridges and strands of galaxies connecting one node to another became known as filaments, threads of galaxies stretched taut across the darkness between them, sometimes running for hundreds of millions of light-years, with only a modest scattering of galaxies to mark their path. Where those filaments and nodes spread out into broader, flatter sheets, the way the Great Wall itself did, astronomers simply called them walls. And the vast, nearly empty regions enclosed within all of this, the open water inside the net, became known as voids. Spaces sometimes stretching for hundreds of millions of light-years, with only the faintest scattering of galaxies to be found anywhere inside them, dark, quiet regions bordered on every side by the walls and filaments that gave them their shape: nodes, filaments, walls, and voids. 4 plain words, but together they described something genuinely new, not a universe of galaxies floating independently through empty space, but a universe organized, connected surface to connected surface, each one shaping and touching the next. A galaxy sitting inside a node was never really alone, because a filament led away from it in one direction or another. A filament was never really an isolated bridge, because it always led, eventually, to another node or spread outward into a wall. Even a void, defined by its emptiness, existed only because something surrounded it, gave it its shape, and held it in place. Every part of the pattern depended on every other part. Within a few short years, this same vocabulary had spread well beyond the small circle of researchers who first coined it, showing up in conference talks, in textbooks, and eventually in the popular press. Wherever anyone tried to describe how the universe was actually built, it replaced an older, far vaguer language of clusters and superclusters scattered here and there, with something more precise, a shared set of terms that let one research team in Massachusetts and another on the far side of the world describe the very same kind of structure in the very same way. Whether they were looking at the Great Wall itself or some entirely different patch of sky many hundreds of millions of light-years distant, the discovery raised an uncomfortable question for cosmology at the time, one that took years to properly work through. For decades, physicists had leaned on something called the cosmological principle, the working assumption that if you looked across a large enough chunk of the universe, it would appear roughly uniform in every direction, without any one region looking dramatically different from any other. It is a reasonable assumption, and it makes the mathematics describing the universe far more manageable to work with. But how could a universe built on that kind of underlying uniformity also contain something like the Great Wall, a single structure so enormous that it dwarfed anything cosmologists had previously dared to imagine? The tension, it turned out, was more apparent than real. Zoom out far enough, averaging over volumes even larger than the Great Wall itself, and the universe does appear close to uniform, exactly as the cosmological principle had always predicted. But zoom into the scale of a few 100 million light-years, the very scale Geller and Hucra had just mapped for the first time in human history, and the universe was anything but smooth. It was intricate, architectural, and startlingly consistent in its own strange way, the same basic pattern of nodes, filaments, walls, and voids turning up again and again, wherever astronomers pointed their instruments next, in survey after survey that followed over the years to come. And that, in the end, was the detail that could not simply be set aside. The slice of sky that Geller, Hucre, and de Laparent had measured was still only a slice, a single thin wedge, cut from an unimaginably larger volume. Chosen mostly because it was a wedge, their telescope could realistically survey within a reasonable stretch of time. It was never meant to be the whole picture, and everyone on the team knew it. And yet the pattern it revealed, this architecture of nodes and filaments and walls wrapped tightly around enormous voids, did not look like a local accident, confined only to that one particular slice of the observable universe. It looked like the edge of something very much larger, something that very likely continued in every direction the telescope simply had not yet been pointed. If a single wedge of sky, only a few 100 million light-years deep, already contained a wall of galaxies large enough to reshape how cosmologists thought about the structure of the entire universe, the obvious question, the one nobody yet had a real answer for, was how much farther this pattern actually extended, what exactly was doing the work of holding it together across such staggering distances, and whether the isolated, island-like feeling every single galaxy gives off from a great distance was, in fact, nothing more than an illusion created by scale. Something was clearly binding these structures firmly into place. Something was reaching across those void-sized gaps, connecting node to filament to wall, in a way that gravity alone, acting only on the stars and gas astronomers could actually see and photograph, did not seem strong enough on its own to explain. Whatever that something truly was, it would take another few decades, and telescopes Geller and Hucre could not have dreamed of in their own working lifetime, to finally begin revealing it. The wedge of sky they had measured was the first thread pulled loose from a far larger fabric, and pulling on any single thread, as anyone who has ever caught one on a nail knows, tends to unravel a great deal more than expected. The next question was never really whether the pattern continued. It was what the pattern was actually made of, and why it had chosen to arrange itself this way in the first place, rather than any of the countless other ways a universe full of galaxies might have settled into place. To answer that question, you have to stop looking at galaxies altogether and go back much further than any galaxy has ever existed, back to a version of the universe so young, so hot, and so nearly featureless that the word galaxy would not have meant anything at all yet. The pattern Margaret Geller and John Hucre had mapped, the nodes, the filaments, the walls, the voids, did not begin with matter clumping together out of nowhere. It began as something almost too small to imagine, a set of differences so faint that for decades scientists could only guess they existed, long before anyone had the instruments sensitive enough to actually confirm it. Every wall, every empty bubble, every glowing knot of galaxies traces its ancestry back to that one impossibly early moment, an inheritance passed down across nearly the entire age of the universe. The oldest light in the universe is not starlight at all. It is something far older and far dimmer, a faint glow that fills the entire sky in every direction, left over from a time roughly 380,000 years after the beginning, when the universe had finally cooled enough for light to travel freely for the first time, instead of being trapped and scattered by a dense fog of charged particles. Astronomers call this glow the cosmic microwave background, and it is, in the most literal sense possible, a baby picture of the universe, showing what everything looked like when it was still almost perfectly smooth. Almost, not quite. And that tiny exception turned out to matter more than anything else in this entire story. Picture that glow spread out across the entire sky at once, mapped the way a flat paper map spreads the whole curved surface of the Earth into a single oval. colored a certain way, that map shows almost nothing at all, a nearly featureless wash of a single shade from edge to edge, because the temperature of this ancient light is astonishingly uniform no matter which direction you look. But turn up the sensitivity of the instrument enough, sharpen the contrast enough, and faint patches begin to appear. Some regions a hair warmer than the average, others a hair cooler, scattered across the whole sky in an intricate, mottled pattern, not unlike the subtle grain visible in a photograph enlarged far beyond its original size. In 1989, NASA launched a satellite called the Cosmic Background Explorer, specifically to study this ancient light in detail. By 1992, the mission's scientists, led by John Mather and George Smoot, announced something extraordinary. Buried within that glow, at a level of precision finer than anything measured before, were tiny variations in temperature from one direction of the sky to another, differences of only a few hundred thousandths of a degree. It does not sound like much. It barely sounds like anything at all. But those two men would go on to share the Nobel Prize in Physics in 2006 for finding it, because those hundred thousandths of a degree were the fingerprints of the very first structure the universe ever produced. Warmer spots marked regions that were, at that unimaginably early moment, very slightly denser than their surroundings. Cooler spots marked regions that were very slightly emptier. Later missions refined the picture further still. First, a NASA probe launched in 2001 that sharpened the map considerably, and then a European satellite named Planck, after the physicist Max Planck, launched in 2009, that sharpened it once again, each one confirming the same basic pattern with greater and greater precision. It was data from that final mission, in fact, that would eventually pin down the precise recipe of the universe's contents, the very numbers described further along in this story. The universe, it turned out, had never been perfectly uniform, not even in its very first few 100,000 years. It had always carried the faint seeds of everything that came later. The reason those faint seeds mattered so much comes down to one of the oldest and most patient forces in nature. Gravity does not care how small a difference is. Give it enough time, and it will find any advantage, however slight, and lean on it relentlessly. A region of the infant universe that started out just 100,000th of a degree denser than its surroundings carried, ever so slightly, a little more gravitational pull than the emptier regions around it. That tiny extra pull drew in a little more surrounding matter. With a little more matter drawn in, the pull grew slightly stronger still, which drew in even more matter, which made the pull stronger again. It is the same principle behind a small snowball rolling down a long, snow-covered hill, gathering more snow with every turn, growing heavier, which lets it gather still more snow, faster, until what began as something you could hold in one hand becomes something far too large to stop. Multiply that same patient, self-reinforcing process across nearly 14 billion years, and 100,000ths of a degree in the infant universe become the towering walls and vast empty voids that Geller and Hucra eventually photographed with their telescope on Mount Hopkins. Working out the details of exactly how that process unfolded, mathematically and rigorously rather than just as a rough intuition, became the life's work of a theoretical physicist named James Peebles, a professor at Princeton University, who spent decades, beginning in the 1960s, building the framework that explained how gravity could take the nearly invisible ripples seen in the ancient light and grow them into galaxies, clusters, and the larger architecture connecting them. Peebles was not chasing headlines. He was doing the slow, careful mathematics that nobody else had fully worked out, describing how matter should behave as the universe expanded and cooled, and predicting, well before anyone had the technology to check, that this exact kind of large-scale structure ought to exist. In 2019, decades after that early work, Peebles was awarded the Nobel Prize in Physics for what the committee described as his theoretical discoveries in physical cosmology. Recognition that arrived only after observation had confirmed what his calculations predicted. He had spent the bulk of his career working quietly with pencil, paper, and later a computer, largely removed from any telescope, treating the universe as a problem to be solved through careful reasoning about how matter and gravity ought to behave under the conditions of an expanding cosmos. It was not an approach that produced dramatic headlines in its own time. It produced something more durable, a working blueprint for cosmic structure that later generations of astronomers, equipped with instruments Peebles never used himself, would spend decades testing point by point against the actual sky and confirming again and again. Peebles's framework explained that structure would grow, but it took another line of theoretical work developed around the same period by the Soviet physicist Yakov Zeldovich to explain why that growth would settle into sheets, filaments, and nodes specifically, rather than simply clumping into round blobs scattered evenly through space. Zeldovich showed, through his own careful mathematics, that a real patch of slightly denser material in the infant universe is almost never a perfect sphere. It stretches a little more in one direction than another, the way a lump of dough rarely comes out perfectly round, no matter how carefully it is shaped by hand. As gravity pulls such a patch inward, it collapses fastest along its shortest direction first, flattening into a broad, thin sheet before the other directions catch up. Somewhat, the way a mattress compresses first under the corner, where the weight presses down hardest. Those flattened sheets, in turn, intersect with neighboring sheets to form the narrower filaments, and filaments intersect with other filaments to form the densest nodes of all. It is a strange, almost paradoxical idea. The very same tiny irregularities that make a young universe less than perfectly smooth are exactly what force matter, billions of years later, into thin sheets and slender threads rather than simple, tidy spheres. A perfectly smooth, perfectly symmetrical universe would have produced no structure at all. It was the imperfections that built everything. But there was a complication buried inside Peebles's own equations, one that would not be resolved for years. The ordinary matter astronomers could actually see through a telescope, the stuff that makes up stars, planets, glowing clouds of gas, and every galaxy ever photographed, simply did not weigh enough to explain the gravity required to build structure this quickly, or to hold galaxies together as tightly as they clearly were held. Something else had to be supplying the missing pull. The first hint of this had actually come decades earlier, in 1933, when the astronomer Fritz Zwicky studied a crowded cluster of galaxies in the constellation Coma and noticed that its individual galaxies were racing around each other far too quickly. Based on the visible starlight alone, the cluster did not have nearly enough mass to hold onto galaxies moving that fast through its own gravity. They should have flown apart long ago. Zwicky proposed that some additional, unseen form of matter must be supplying the extra gravitational glue, though his idea sat largely unexamined for decades afterward. The case became impossible to ignore in the 1970s, when the astronomer Vera Rubin, working with her colleague Kent Ford, carefully measured how fast stars orbit around the outer edges of spiral galaxies, patiently gathering data on one galaxy after another over the course of years. By every conventional expectation, stars far from a galaxy's bright center should orbit slowly, the same way outer planets in our own solar system circle the sun at a leisurely pace, compared to the inner planets. Instead, Rubin and Ford found that stars near the edges of these galaxies moved almost as fast as stars much closer to the center, as though some invisible mass, well beyond what any telescope could see, were wrapped around each galaxy and pulling on those outer stars far more strongly than the visible starlight alone could account for. Rubin's careful, repeated measurements, galaxy after galaxy, made the case undeniable in a way Zwicky's single cluster never quite had. She kept measuring long, after most colleagues would have considered the case already made, methodically ruling out simpler explanations one at a time, until the pattern held so consistently across so many different galaxies that no other honest conclusion remained available. Astronomers gave this unseen material a name: dark matter, not dark because it absorbs light, but dark because it does not interact with light at all, neither emitting it, nor reflecting it, nor blocking it, detectable only through the gravity it exerts on everything around it. That invisible material turned out to be the true scaffolding behind everything Geller and Hukra had mapped. Stars and galaxies are bright, and so they are what any camera or telescope naturally captures, but they represent only a small fraction of the actual mass involved in building the pattern of nodes, filaments, walls, and voids. Dark matter makes up roughly 85% of all the matter in the universe, vastly outweighing every star, every planet, and every glowing cloud of gas combined. It was dark matter's gravity, not the gravity of visible stars, that did the patient work of gathering those infant density variations into the towering structure later generations of astronomers would eventually photograph. The galaxies themselves are almost an afterthought, bright decorations scattered along a framework built overwhelmingly out of something no telescope has ever directly seen. Astronomers do have one further way of confirming that this invisible scaffolding truly sits where the theory says it should, even without ever detecting it directly. Massive clumps of matter, visible or not, bend the path of light passing near them, in exactly the way a heavy stone dropped into calm water bends the ripples that pass around it. Light from a distant galaxy, on its way to Earth, sometimes bends slightly as it passes near a foreground concentration of matter along the way, arriving stretched or duplicated or smeared into an arc. By carefully measuring exactly how much bending occurs, astronomers can work backward and calculate how much mass must be sitting in that foreground region, whether or not any of it shines. Applied across the sky, this technique consistently reveals concentrations of mass far exceeding what any visible galaxy or cluster could account for on its own, sitting in precisely the locations the cosmic web's own structure would predict. The scaffolding does not glow, and it never will, but its fingerprints show up wherever astronomers know to look for them. There is a second, entirely different way scientists have tested whether Peebles and Zeldovich had it right, one that involves no telescope at all. Starting in the early 2000s, teams of astrophysicists began feeding the basic ingredients, the tiny temperature variations measured in the ancient light, the known behavior of gravity, and an estimate of how much dark matter and ordinary matter the universe contains into some of the largest computers available, and simply let the resulting virtual universe run forward across a simulated 14 billion years. One such effort, known as the Millennium Simulation, tracked more than 10 billion individual particles of virtual dark matter as they pulled on each other across that entire span of simulated time. What emerged on the screen once the simulation finished was not a random scatter of blobs. It was a lattice of nodes, filaments, walls, and voids, startlingly similar in overall appearance to the actual structure astronomers had already mapped through their telescopes. A theory built on pencil and paper decades earlier tested first against the ancient light and then against the real distribution of galaxies, now passed a third test entirely, recreated from scratch, inside a machine, using nothing but the basic rules of gravity and the faint imperfections recorded in the universe's oldest photograph. Watching those simulations unfold, frame by frame, across a computer screen, drove home something that a printed map alone had never quite captured. The structure did not simply sit still. It writhed and reorganized itself, slowly across billions of simulated years, threads thickening here, thinning there, nodes merging as filaments fed them more and more material. The entire pattern behaving less like a fixed architecture and more like a single, slowly shifting, interconnected fabric. It was around this same period, as these simulations and the growing catalogue of surveyed galaxies reinforced each other, that researchers began referring to the whole pattern by a single, unified name, moving beyond the separate terms, nodes, filaments, walls and voids, to describe the entire interconnected structure at once. They called it the cosmic web, a name that stuck precisely because nothing else quite captured it, not a scattering of separate objects, but one continuous, woven structure, stretching across the observable universe. Once you add dark matter into the picture, the full recipe of the universe looks strange enough to sound almost like a riddle. Roughly 68% of everything that exists is something even stranger still, called dark energy. A mysterious pressure that pushes space itself to expand faster over time rather than pulling things together the way gravity does. Nobody fully understands what dark energy actually is, only that its effects are measurable and consistent, showing up in how quickly distant galaxies recede from us and from each other. Roughly 27% is dark matter, the invisible scaffolding just described. And the ordinary matter, the stars, the planets, the gas, the galaxies, every telescope image ever captured, every human being who has ever lived, amounts to only about 5% of the total. We are, in the most literal sense, a minority report on the contents of our own universe. That small 5% slice carried a mystery of its own, one that took a different kind of instrument entirely to untangle. Careful calculations based on the early universe, worked out from how hydrogen and helium formed in the first few minutes after the beginning, told physicists precisely how much ordinary matter ought to exist today, a figure confirmed independently by the same ancient light that revealed the density variations in the first place. But when astronomers tried to add up all the ordinary matter they could actually locate directly, counting the mass of every star in every galaxy, along with every visible cloud of gas between them, the total came up far short, missing roughly half of what the early universe calculations said should be there. For years, this discrepancy was known, somewhat dryly, among cosmologists as the missing baryon problem. Baryon being the technical name for the particles that make up ordinary matter, protons and neutrons, rather than the more exotic, dark variety. Decades passed without a clean answer. The missing matter had not vanished. Physicists were confident of that much, since nothing in known physics could simply erase it. It had to be somewhere. It was just too thin, too dark, and too widely scattered for any ordinary telescope, built to gather starlight rather than to detect gas, so diffuse, it barely qualifies as gas at all. To pick out, the tool that finally tracked it down came from an entirely unexpected corner of astronomy. In 2007, the astronomer Duncan Lorimer, working with a student, combing through archived data from the Parkes Observatory in Australia, a large dish telescope perched in the sheep country of New South Wales that had spent years listening patiently to the radio sky, noticed something odd buried in old recordings, an intensely bright, extraordinarily brief flash of radio waves, lasting only a few thousandths of a second, that had clearly come from far beyond our own galaxy. Whatever produced that single flash had released an almost unimaginable burst of energy within that fraction of a second, far more power than anything else astronomers typically observe over such a short span of time, and it had done so somewhere out among other galaxies, not anywhere nearby. Nobody could yet explain what produced it, and in truth, the exact source of these flashes, now called fast radio bursts, remains only partly understood even now, with leading candidates including the collapsed, magnetically supercharged remnants of dead stars. But astronomers quickly realized that regardless of what caused them, the bursts themselves carried something enormously useful buried in their timing, and once the first one was found, patient searches through more archived data and eventually dedicated new surveys built specifically to catch more of them began turning up dozens, then hundreds more, scattered all across the sky. Picture a marching band stepping off together at the start of a long parade route, every instrument in step, every note landing at exactly the same instant. By the time that same band reaches the reviewing stand at the far end of a very long route, the group is no longer quite so tightly bunched together. Different sections drift slightly out of step with each other over that distance, spreading out just slightly by the time they arrive. A fast radio burst behaves in a strikingly similar way as it crosses the vast distances of intergalactic space. It leaves its source as a single tightly bunched flash containing many different radio wavelengths all together. But as it travels for millions or even billions of years through the thin, ionized gas drifting between galaxies, the different wavelengths within that flash are each slowed down by a very slightly different amount, causing them to spread apart, arriving at our telescopes not all at once but stretched out over a measurable delay. The amount of that spreading depends directly on how much ionized gas the burst passed through along the way. A burst that crossed a great deal of gas arrives noticeably more spread out. A burst that crossed comparatively little arrives closer to its original, tightly bunched shape. In this way, without ever detecting the gas directly, astronomers could measure, indirectly but reliably, exactly how much of it stood between us and the source of each burst. In 2020, the astronomer Jean-Pierre Macquart led a team that used this exact technique on a carefully chosen sample of these bursts, ones whose home galaxies could be identified with confidence rather than only their rough direction on the sky, to conduct the first rigorous census of the universe's ordinary matter using this new method. Pinning down a burst's home galaxy mattered enormously, because only then could the team calculate a reliable distance for each burst, and only with a reliable distance could the amount of spreading in its signal be translated into an actual measurement of how much gas it had passed through along the way. Working through more than 20 of these carefully localized bursts, Macquart's team added up the implied gas along each line of sight and compared the total against the figure predicted from the early universe. The results matched those early universe calculations closely, confirming that the long-missing baryons had never actually vanished at all. They were simply spread so thin, so diffusely, across such enormous volumes of intergalactic space that no telescope built to gather starlight had ever been able to register them. Macquart did not live to see the full impact of that discovery unfold. He passed away suddenly only shortly after the work was completed, and colleagues who continued building on his method have made a point, in the years since, of crediting the census that finally accounted for the universe's missing matter to the astronomer who found it. More recent work has gone even further, using a much larger sample of these bursts to work out not just how much of that ordinary matter exists, but precisely where it actually resides. A study published in 2025, led by researchers building directly on Marquardt's approach, drew on a far larger collection of localized bursts than had ever been available before, and carefully sorted the missing baryons among the different environments they might occupy, tucked inside galaxies themselves, surrounding galaxies in extended halos of gas, or spread through the vast, thin material drifting between galaxies entirely. Untangling those three possibilities required more than just distance and total gas along each line of sight. It required comparing dozens of bursts crossing many different kinds of environments and carefully modeling how much each environment ought to contribute before the individual pieces could be separated out with any real confidence. The answer, once the work was done, was strikingly one-sided. Roughly 3/4 of all that ordinary matter turned out to be sitting in that last category, diffuse, ionized gas filling the space between galaxies rather than sitting inside them, matching, almost point for point, the same filaments and walls that Geller and Hukra's survey had already revealed through an entirely different method decades earlier. The invisible dark matter supplied the gravitational scaffolding. This diffuse gas, it turned out, supplied much of the actual visible matter budget, flowing along that scaffolding the way water moves through a network of rivers and streams carved into a landscape, feeding every settlement built along its banks. Taken together, this gave cosmologists an extraordinarily complete picture, built without a single photograph of the structure itself. They knew the tiny thermal fingerprints in the ancient light where it all began. They knew, from Peebles's careful mathematics, exactly how gravity would take those fingerprints and grow them across billions of years. They knew, from Zwicky and Rubin's patient measurements, that the true scaffolding holding it all together was an invisible form of matter outweighing every star combined. And they now knew, from the timing of radio flashes crossing unimaginable distances, precisely where the universe's remaining ordinary matter had been hiding all along. Every piece fit, every calculation lined up with the next. And yet, for all of that, something essential was still missing from the story, something no amount of theory, no satellite measuring ancient light, and no radio burst crossing the darkness had yet managed to provide. Every single piece of this picture had been assembled indirectly. The temperature map came from measuring light, not from watching structure form. The mathematics came from a chalkboard and a calculator, not from a telescope. The dark matter came from timing the orbits of stars and bending the paths of distant light, never from a direct image of the material itself. Even the gas, finally located within the great filaments, had been measured only by how it delayed a radio signal passing through it. The way you might infer a fog bank exists by timing how long a foghorn's sound takes to reach a ship without ever once actually seeing the fog. Nobody had ever actually pointed a telescope at one of these filaments and simply watched it glow with its own faint light, gathered directly, the way astronomers had always gathered the light of a star or a galaxy. The theory was airtight. The math was decades old and thoroughly tested, but an entire architecture connecting every galaxy in the visible universe remained, in the truest sense, unseen. That gap between knowing and seeing did not close quickly, and it did not close easily. For decades, the closest anyone came to actually observing a filament was watching its shadow, when the light from an extremely distant, extremely bright object, typically the blazing core of a galaxy with an active black hole at its center, happened to pass directly through a foreground filament on its way to Earth. Astronomers could sometimes detect faint absorption lines in that light, dark notches, marking wavelengths where the intervening gas had quietly swallowed a portion of the signal passing through it. It worked, in a rough sense, but it depended entirely on a bright background light source, lining up almost perfectly behind a filament, a stroke of cosmic luck that limited astronomers to essentially one thin, one-dimensional slice. Through the gas at a time, a single beam of light threading a needle across billions of light years. Astronomers built entire careers refining this shadow reading technique, cataloging thousands of these faint absorption notches, patiently assembling statistical evidence for the gas-filling intergalactic space. And the technique genuinely earned its keep, contributing real and lasting knowledge about how much gas exists and roughly how it is distributed. But a shadow, however carefully measured, only ever tells you that something sits between the light and the observer. It cannot show you the shape of the thing itself, its width, its curve, the way it bends and connects to its neighbors. Nobody had managed to capture the gas itself, glowing on its own, spread out across its true shape, the way you would photograph a nebula or a galaxy directly rather than only inferring its presence from a shadow it happened to cast. The challenge came down to brightness, or rather the almost complete absence of it. A filament of the cosmic web is, by any ordinary standard, close to nothing at all, a whisper of hydrogen gas spread across millions of light years, so thin that a room the size of a family dining room might contain only a handful of atoms. Any light that gas gives off on its own is correspondingly faint, dimmer than almost anything else astronomers routinely attempt to photograph, closer in brightness to the glow of a single distant candle than to the light of a star. Capturing it required not just a large telescope, but an extraordinarily patient one, willing to keep its shutter open, in effect, for far longer than any single night could provide. It was not unlike the earliest days of photography itself, when a portrait required a subject to sit rigidly still for long minutes at a time, sometimes braced with a hidden metal stand just to prevent the slightest tremble, simply so enough faint light could accumulate on the plate to form a usable image. Astronomers chasing the cosmic web's own glow needed something similar, an exposure held open not for minutes, but for hundreds of hours, spread out across many separate nights, all of it stacked together afterward into one single, patiently assembled picture, with every passing cloud, every stray beam of moonlight, and every flicker of the instrument's own electronics carefully subtracted out before the faint signal underneath could finally be trusted. An early step toward that goal came in 2019 when the astronomer Hideki Umehata and his colleagues, using the Subaru telescope in Hawaii, examined a crowded, still-forming region of the young universe, known to contain several actively growing galaxies, packed unusually close together, and detected extended glowing gas stretching across roughly 1 million light-years, threading directly between them. It was a genuine breakthrough, the first time anyone had captured this kind of extended glow directly, rather than only inferring it from an absorbed shadow, and it strongly suggested that filaments really did glow on their own, faintly, if you knew how to gather enough of their light. The detection relied on a particular wavelength of light given off naturally by hydrogen gas when it is gently excited by radiation from nearby young, hot stars and active galaxies, a signal astronomers can filter for specifically using the right kind of specialized instrument, much the way a radio can be tuned to isolate one station out of a crowded dial. But the image remained comparatively blurred, low in resolution, more a confirmation that the glow existed than a detailed picture of its true structure, closer to a shape glimpsed through a pane of frosted glass than a clean photograph. Sharpening that smudge into something with real, measurable shape would take 6 more years and an entirely different kind of instrument. The image that finally delivered both arrived in 2025. A team led by the astronomer Davide Tornotti working with colleagues from the University of Milano Bicocca and the Max Planck Institute for Astrophysics, pointed an instrument called MUSE, mounted on the Very Large Telescope operated by the European Southern Observatory high in the Atacama Desert of Chile, at a patch of sky already known to contain two extremely distant, extremely active galaxies, each one powered by a supermassive black hole devouring material at its center. Rather than waiting for a lucky, brief alignment with some unrelated background light source, the team simply pointed their instrument at that patch of sky and left it there, gathering light patiently, night after night, until the accumulated exposure stretched past 100 hours. MUSE offered something the earlier shadow reading technique never could: the ability to gather not just brightness, but an entire spectrum of color at every single point across the field of view simultaneously, effectively producing thousands of tiny measurements at once, rather than one narrow beam. That capability turned out to be exactly what was needed to finally separate the faint true glow of hydrogen gas from the ordinary background noise of the night sky and the telescope's own instruments. When the team finally processed the result, painstakingly subtracting away everything that was not the filament itself, a thin glowing bridge of gas emerged directly from the data, stretching between the two galaxies across a distance of roughly 3 million light-years, glowing faintly under its own light rather than merely casting a shadow across someone else's. The light captured in that image had been traveling for just under 12 billion years to reach the telescope, meaning the two galaxies and the filament connecting them appeared exactly as they had looked when the universe itself was only about 2 billion years old. A portrait of the cosmic web taken not long, in cosmic terms, after it had first begun assembling itself out of the ancient light's faint thermal seeds. It was, by any honest measure, the sharpest direct image of a single filament ever captured, and it settled a question that had lingered since Geller and Hutra first plotted their slice of the universe decades earlier. The gas was there, exactly where the theory said it should be, glowing softly on its own, not merely implied by the positions of galaxies, not merely inferred from a temperature map of ancient light, not merely calculated from the delay of a passing radio flash, but gathered directly, photon by photon, the same patient way astronomers had always gathered the light of any star or any galaxy. In the finished image, the filament appears as a soft, elongated haze bridging the two brilliant points of the galaxies at either end, subtly brighter along its central spine and fainter toward its edges, curving very slightly rather than running in a perfectly straight line, the same gentle curvature Zeldovich's old mathematics had predicted decades before anyone had a telescope capable of confirming it. The image showed the filament with enough clarity to measure its width as well as its length, revealing a structure narrower and more tightly defined than some earlier theoretical models had predicted. A genuine new piece of information rather than simply a confirmation of what was already assumed. The cosmic web had a face at last, even if that face remained fainter than almost anything else in the night sky, and even if capturing it had required patience measured in years of proposal writing and hundreds of hours of careful, uninterrupted observation on one of the finest telescopes ever constructed. Word of the result traveled quickly through the small, tightly connected world of observational cosmology. Colleagues who had spent entire careers relying on the older shadow reading method, and others who had spent years refining the theoretical predictions Peebles and Zeldovich first laid out decades earlier, found themselves looking at the same picture, an actual photograph, rather than a chart of temperatures or a table of statistics, showing gas arranged in precisely the filamentary shape their equations had always described. Skepticism, healthy and expected in any field, gave way relatively quickly this time, in part because the result did not stand alone. It arrived already surrounded by decades of independent confirmation, the ancient light, the galaxy surveys, the bent starlight, the timed radio flashes, all of it already pointing toward the same underlying structure. The photograph did not have to persuade anyone that the cosmic web was real. It only had to show, at last, what everyone already suspected it looked like. A single photograph of a single filament, however striking, only answers one question at a time. It does not tell you what the entire architecture looks like stitched together across the whole visible universe, and by the middle of this decade, several major efforts were already racing to answer exactly that, using an approach closer to Geller and Hukra's original method than to Tornotti's, but carried out at a scale neither of them could have imagined from their small mountain observatory decades earlier. Where a single deep image demands patience aimed at one tiny patch of sky, mapping the entire structure demands the opposite instinct entirely, breadth rather than depth, speed rather than lingering exposure, a willingness to measure something about millions of galaxies quickly rather than everything about one filament slowly. Both approaches were necessary. Neither could substitute for the other. The most ambitious of these efforts operates from Kitt Peak National Observatory in Arizona, where an instrument called the Dark Energy Spectroscopic Instrument, mounted on a telescope first built in the 1970s and since heavily modernized, has spent recent years measuring the redshift and therefore the true distance of tens of millions of galaxies and distant quasars at once, using thousands of tiny robotic positioners that each aim a hair-thin fiber optic cable at a single galaxy's light, adjusting themselves automatically between exposures to gather as many redshifts as possible in a single night. Each of those small robotic arms works independently, swinging into position within seconds under its own tiny motor, arranged together by the thousands across the telescope's focal plane like an enormous, densely packed pincushion, so that a single exposure of the night sky can capture the spectrum, and therefore the distance, of thousands of separate galaxies simultaneously rather than one at a time. Where Geller and Hukra's project measured one galaxy's light at a time across an entire career, spread over a decade of patient effort, this instrument gathers thousands simultaneously, night after night, compressing what once took a career into what now takes a single, clear evening on the mountain. In April of this year, the project completed its planned 5-year survey, having measured the redshifts of more than 47 million galaxies and quasars, along with millions of individual stars within our own galaxy, producing the largest and most detailed three-dimensional map of the universe ever assembled, stretching across more than 11 billion years of cosmic history. The survey is not finished. Observations are already scheduled to continue for several more years, expanding the mapped area even further beyond what has already been completed. Buried inside that enormous map sits a genuine puzzle, one still being carefully worked through rather than settled. Cosmologists use the pattern of galaxy clustering within surveys, like this one, to measure how the universe's expansion has changed over time, and by extension, how dark energy, the mysterious pressure pushing space apart, may have behaved across cosmic history. Early results released in 2024 and refined further the following year hinted that dark energy might not be perfectly constant after all, that its strength may have shifted somewhat over billions of years rather than remaining fixed the way the simplest models assume. The hint is intriguing, and it has generated a great deal of careful discussion among cosmologists. But it has not yet reached the level of statistical certainty that physicists require before calling something a confirmed discovery rather than a promising lead. Physicists are, as a rule, a cautious group when it comes to overturning a model that has otherwise worked remarkably well for decades, and rightly so. since earlier apparent anomalies in cosmology have sometimes faded away once more data arrived. More data, gathered over the coming years as the survey continues, will be needed before anyone can say with confidence whether dark energy has truly been changing, or whether the hint will fade as the map grows larger and more complete. Either answer would matter enormously for understanding the long-term fate of the very structure this entire story has been describing, since a dark energy that grows stronger over time would eventually pull the cosmic web's own filaments apart, while a dark energy that weakens might allow the structure to grow richer and more tightly bound as the eons pass. A second major effort has been unfolding from orbit rather than from a mountaintop, for reasons that have everything to do with Earth's own atmosphere. Even the clearest mountaintop air still blurs and shimmers starlight slightly on its way down to a ground-based telescope, smearing the crisp edges of distant galaxies just enough to make the extremely subtle distortions caused by foreground dark matter difficult to measure with real confidence. Placing a telescope above that atmosphere entirely removes the problem. In July of 2023, the European Space Agency launched a space telescope named for the ancient Greek mathematician Euclid, designed specifically to measure the shapes and positions of billions of galaxies across roughly a third of the entire sky, watching for the same subtle bending of background light by foreground mass that reveals dark matter's hidden distribution with a clarity no ground-based instrument could reliably match. Where a ground-based survey, like the one operating from Arizona, measures distance through the stretching of light, Euclid's approach leans more heavily on measuring the faint distortion in the shapes of countless background galaxies, each one subtly stretched or smeared by whatever mass, visible or invisible, happens to sit between it and the telescope, a separate and complementary way of tracing where mass actually sits across the sky. The mission released its first substantial batch of public data in March of last year, covering several dedicated deep fields packed with distant galaxies alongside a wider first slice of ordinary sky, followed by a second release only weeks before this recording, in June of this year, each one covering a larger swath of sky than the last, gradually filling in a mosaic that will eventually stretch across roughly 1/3 of the entire visible sky once the mission concludes. Its first dedicated results, specifically addressing dark energy, are expected this coming October, results that, combined with the ground-based survey's own findings, should either strengthen or weaken that same hint of a dark energy that changes rather than stays fixed. Two entirely different instruments, one measuring light stretched by cosmic expansion, the other measuring light bent by cosmic mass, converging on the very same question from two different directions at once, each one serving as an independent check on whatever the other happens to find. Neither team designed its instrument in isolation from the other. Astronomers on both projects have spent years planning how their two very different catalogues of galaxies, one gathered from a mountaintop in Arizona, the other gathered from an orbit far beyond the Moon, might eventually be layered directly on top of each other, matching individual galaxies between the two datasets so that a single object's distance, its shape, and the way its light has been subtly bent by everything sitting between it and Earth can all be studied together rather than separately. That combined catalogue does not yet fully exist. Building it carefully, galaxy by galaxy, remains ongoing work, but the outline of what it will eventually contain is already visible in the data gathered so far, a single unified record of where matter, visible and invisible, actually sits across a meaningful fraction of the observable universe. A survey of this size creates its own kind of challenge, one that has nothing to do with telescopes or gas or gravity at all. Measuring the redshifts of 47 million galaxies produces an amount of raw information that no team of human beings could ever hope to examine object by object, the way an earlier generation of astronomers once pored over individual photographic plates by hand. Instead, the incoming data streams directly into powerful computing centers where automated software sorts, calibrates, and catalogs each measurement long before any person ever looks at it, flagging only the small fraction of results unusual enough to warrant closer human attention. It is a strange inversion of how astronomy worked for most of its history, when a single trained eye, squinting at a single glass plate, was the final word on whether a smudge of light counted as a galaxy at all. Now, the telescope gathers more in a single night than earlier generations gathered across entire careers, and the real bottleneck has shifted from collecting the light to making sense of everything the light contains. Margaret Geller herself, well into the era when these newer surveys were taking shape, had spent her own career pushing against exactly this kind of bottleneck, one patient galaxy at a time, and lived to see the field she helped found scale up by a factor of thousands within the span of a single working lifetime. None of these efforts operate in isolation from the others, and that turns out to matter a great deal. A single deep image proves the gas glows. A spectroscopic survey of tens of millions of galaxies proves the overall shape repeats consistently across enormous volumes. A space telescope measuring the bending of background light proves the invisible mass sits precisely where that shape says it should. An X-ray survey of hot cluster gas proves the densest nodes really do contain as much material as the theory demands. Each method has its own particular blind spots, its own particular sources of error, its own particular limitations in what it can and cannot measure directly. But those blind spots rarely overlap between one method and the next, which means that when 4 or 5 entirely different techniques built by different teams using different instruments, funded by different countries, all converge on the same basic picture, the confidence in that picture grows far stronger than any single result could ever provide on its own. This is not a story about one lucky photograph settling an old argument. It is a story about an entire toolkit finally maturing all at once, each tool checking the other's work. Once the ground-based survey completes its extended observing schedule and the orbiting telescope finishes covering its full portion of the sky, likely within the next few years, cosmologists expect to have, for the first time, a map detailed enough to trace the cosmic web's largest filaments individually by name across a meaningful fraction of the observable universe, rather than only in scattered, isolated patches surveyed one at a time. All of this mapping, whether from a single sharp photograph of one filament or a spectroscopic census of tens of millions of galaxies, eventually needs landmarks, familiar points within the structure that give a sense of scale and orientation, the way a traveler needs at least a few named towns marked on an otherwise overwhelming map. Our own home within the cosmic web carries a name of its own. In 2014, the astronomer Brent Tully and his colleagues, tracing the motions of galaxies across our surrounding region of space rather than simply their distances, identified the full boundaries of the supercluster containing our own Milky Way by mapping which galaxies were gravitationally flowing toward the same shared region and which belonged to some separate, neighboring flow entirely. The result was a sprawling node within the web, spanning roughly 520 million light-years and containing on the order of 100,000 galaxies. They named it Laniakea, a Hawaiian word meaning immeasurable heaven, chosen deliberately to honor the Polynesian navigators who once crossed the vast Pacific Ocean using nothing but the stars, the currents, and careful memory for guidance, without instruments of any kind. The Milky Way sits well out toward one edge of this structure, one address among 100,000 others, all of it slowly flowing along filaments toward a shared gravitational center astronomers call the Great Attractor, a concentration of mass whose own pull can be measured in the motion of every galaxy nearby, our own included, even though the attractor itself sits partly hidden behind the crowded disk of our galaxy and remains difficult to observe directly. Even a structure the size of Laniakea, though, is only a modest knot compared to what a more recent survey has revealed, looking out somewhat farther still, well beyond the boundaries of our own immediate supercluster, into a region of the surrounding universe, distinct from Laniakea, rather than some larger container holding it, a separate node entirely within the same unbroken web. In early 2025, the astronomer Hans Boehringer and his colleagues at the Max Planck Institute for Extraterrestrial Physics, cataloging galaxy clusters across nearly the entire accessible sky using data gathered by an orbiting X-ray observatory sensitive enough to detect the hot, glowing gas that fills the space around and between clustered galaxies, identified an even larger structure stretching across roughly 1.4 billion light-years, a single connected chain of clusters and filaments containing an estimated 200 quadrillion times the mass of our Sun. They named it Quipu, after the knotted, colored cords once used by Andean civilizations to record numbers and information long before any written script reached that part of the world, a fitting name for a structure that resembles, in the team's own three-dimensional maps, a long central cord with numerous shorter strands branching off along its length. By most measures available today, Quipu stands as the largest single structure yet reliably identified in our surrounding region of the universe, though even here, honesty requires a pause. Some cosmologists studying Quipu have raised a fair question about whether it truly counts as one bound, coherent object, gravitationally holding itself together the way a single galaxy cluster does, or whether it more closely resembles a large gathering of cars filling every space in a stadium parking lot on the day of a big game, densely packed together for one particular afternoon, without any of them being permanently attached to one another. As the universe continues expanding, some portions of Quipu's sprawling structure may eventually drift apart, rather than remaining bound as a single unit indefinitely. A possibility the researchers who first described it acknowledged openly in their own published work. The name and the record it currently holds may prove durable. Whether the object itself remains truly whole across the deep future is a separate question entirely, one the data available today cannot yet fully answer. Between one sharp photograph of a single glowing thread and a spectroscopic map spanning tens of millions of galaxies, between our own modest address within Laniakea and a structure as vast as Quipu, the tools now exist, for the first time in the history of astronomy, to do something no single survey or single image could ever manage alone: assemble a genuinely complete picture of the architecture connecting every galaxy human beings have ever observed. The pieces gathered so far, the direct image, the redshift map, the named superstructures, the lensing surveys still filling in around them, are no longer separate lines of evidence pointing loosely in the same general direction. They are converging, piece by piece, into a single connected structure large enough to contain the Milky Way, Laniakea, Quipu, and everything currently being mapped between them. What remains is not proving that the structure exists. That question has been closed for some time now, confirmed independently more ways than any one team could have anticipated when Geller and Hutra first plotted their thin wedge of sky, back when a single galaxy's distance took an entire night's patient work to measure. What remains is something quieter and in some ways more difficult, understanding what a structure shaped exactly this way, built exactly this patiently out of gravity and faint hydrogen gas, actually resembles, once you finally step back far enough to see the whole of it at once, rather than one filament or one survey at a time. Every map completed so far has answered a narrower question than that one, each contributing its own small, careful piece to a picture still being assembled. None of them, on its own, has yet had to answer the broadest one, the question of what this particular shape, out of all the shapes a universe full of galaxies might conceivably have settled into, most truly calls to mind, including the small, bright knot of matter that happens to include every person who has ever lived. The answer to that question came from a place nobody in astronomy was expecting, not from another telescope, not from a bigger simulation or a deeper survey or a sharper image. It came from setting the finished maps of the cosmic web next to an entirely different map, one that had nothing to do with space at all, and noticing something neither field had gone looking for. Astronomers had spent decades perfecting their ability to render the cosmic web visually, coloring nodes bright and voids dark, rotating three-dimensional models on a screen, trying to find some way of presenting the structure that would let another person grasp its shape at a glance rather than through pages of coordinates and measurements. Every attempt ran into the same basic obstacle. Nothing else in ordinary experience looks quite like it. A mountain range has a silhouette a person can sketch from memory. A river system has a shape every schoolchild learns to recognize on a map. The cosmic web resembled neither, a structure too vast for geography and too irregular for simple geometry, difficult to describe to anyone who had not spent years staring at simulations of it firsthand. It turned out that the clearest possible reference for what they had built was never going to come from inventing a new kind of picture. It was already sitting, quite literally, inside the skull of every person who might ever look at one. In 2020, an Italian astrophysicist named Franco Vazza, whose own research at the University of Bologna involved building and studying simulations of exactly the kind described earlier in this story, teamed up with Alberto Folletti, a neurosurgeon whose daily work involved the physical structure of the human brain rather than the structure of the universe. It was an unusual pairing of specialties, the kind that rarely ends up sharing a research paper, one man spending his career among galaxies too distant to ever visit, the other spending his among the folds of a single living organ small enough to hold in two hands. But each of them had spent years staring at a particular kind of picture, a tangle of dense clusters joined by long branching threads, and each of them, independently, had noticed how strongly it resembled the others. Between them, they had access to two of the most complex networks known to exist. One was a computer simulation of the cosmic web, its nodes, filaments, and voids built up from the same physics already described, gravity acting patiently on matter across billions of years. The other was a detailed map of the brain's own network of neurons, the branching cells that carry every thought, memory, and sensation a person ever has, connected to one another by trillions of individual junctions called synapses, with the brain as a whole containing something on the order of 86 billion of these neurons, each one linked to thousands of others. Set side by side as pictures, the resemblance is almost startling, Both of them a lattice of dense clusters linked by long, thin, branching strands with wide empty gaps in between. But a passing resemblance in a photograph is one thing. Vaza and Folletti wanted to know whether the similarity held up under actual measurement, or whether it was simply a trick of the eye, the kind of pattern the human mind is prone to seeing everywhere, whether it is truly there or not. So they measured it properly, the way any careful scientist would, translating both structures into the same mathematical language so that a fair comparison actually became possible. They analyzed how many connections typically link one node to its neighbors in each network, how tightly clustered the connections tend to be in different regions, and how efficiently each entire system links its most distant points together, a property mathematicians sometimes call the network's small world character, meaning how few steps it actually takes, on average, to travel from one distant corner of the structure to another, without following every single connection in between. To make sure the comparison meant something, they measured the same properties in other, deliberately different kinds of networks as well. Systems like airline route maps connecting major cities, or the branching patterns of a tree's own root system spreading through soil, structures that share a superficial resemblance to both the cosmic web and the brain when you first glance at a picture of them, dense hubs joined by thinner branching connections. Those comparison networks, tested the same careful way, did not match nearly as closely. Across a whole range of these measurements, the cosmic web and the brain's own neural network turned out to be remarkably similar, far closer to each other statistically than either one was to those other kinds of networks used for comparison, which shared a superficial resemblance to both but not the same deeper numbers. The similarity held even though the two networks differ in scale by roughly 27 orders of magnitude, a gap so large that ordinary numbers struggle to express it honestly. The cosmic web outsizing a single neuron by a factor that would still be written with dozens of zeros, and it held even though the two networks are governed by entirely different physical rules. Gravity built one of them, slowly, over nearly 14 billion years, acting only through attraction, pulling matter inward toward denser regions. Something else entirely, electrochemical signaling shaped by hundreds of millions of years of evolution, built the other, favoring connections that let information travel quickly and efficiently between distant parts of a living brain. It is worth pausing on what this finding does and does not actually mean, because it is the kind of result that invites exaggeration if you let it. In the years since the study appeared, it has occasionally been retold in more excitable terms than the original research ever supported. The idea stretched into suggestions that the universe itself might be some kind of vast, thinking mind, or that gravity and thought were secretly the same phenomenon wearing two different disguises. None of that follows from what Vaza and Folletti actually measured, and neither of them ever claimed that it did. It is easy to understand the temptation. A genuine, carefully measured similarity between the largest structure ever confirmed to exist and the very organ doing the confirming has an undeniable poetic pull to it. The kind of detail that seems almost too fitting to be coincidence. But poetic pull is not evidence, and the honest reading of the data resists the more dramatic version of the story, even while it keeps the more modest one fully intact. The similarity they documented is structural and statistical, a shared pattern in how each network happens to be organized, not evidence that the universe is thinking, planning, or aware of itself in any sense a neurosurgeon would recognize from an actual living brain. Gravity is not electrochemistry. A filament of hydrogen gas does not fire a signal the way a neuron does, and nothing in the cosmic web processes information, forms a memory, or experiences anything at all. There is no evidence from this study or any other that the structure connecting every galaxy in the visible universe is in any sense alive, aware, or purposeful. What the two researchers actually demonstrated was narrower than that, and in its own quiet way just as remarkable. That two of the most complex networks known to exist, one shaped by gravity acting on dark matter across cosmic time, the other shaped by evolution acting on living cells across a single lifetime, arrived at strikingly similar solutions to what may simply be the same underlying mathematical problem: how to connect an enormous number of separate points as efficiently as possible, using the least material to cover the most ground, while still keeping every part reachable from every other part. Nature appears to have solved that particular problem more than once, using completely different tools each time, arriving at a similar answer regardless. Engineers designing communication networks, transportation systems, and power grids have long known that efficient networks tend to converge on broadly similar shapes for purely mathematical reasons, regardless of what they are built from or what purpose they ultimately serve. So, finding that same underlying shape in both a living brain and the largest structure in the universe may say less about either one specifically and more about what efficient connection itself simply requires, wherever it happens to occur. That, on its own, without any need for embellishment, is a genuinely interesting fact about how efficient networks tend to organize themselves, whether they are built from stars or from cells. Even the raw proportions echo each other in a way that is easy to find charming without needing to find it mystical. Roughly 70% of the human brain's mass is water, a passive, structural presence, rather than the part doing any actual thinking. Roughly 70% of the universe is dark energy, a diffuse presence that does no active work in building structure at all. In both cases, the part carrying the information, the neurons in one case, the ordinary matter gathered into stars and galaxies in the other, makes up only a modest fraction of the whole. A minority component, doing the majority of the interesting work. It is a coincidence of proportion, not a hidden message, but it is the kind of coincidence that makes a careful person look twice, and then, having looked twice, set the coincidence gently aside and return to what the data can actually support. The published study itself was careful on exactly this point, framed throughout as a structural comparison between two networks rather than a claim about consciousness or design, the modest, deliberately unglamorous language of a genuine scientific result, rather than a headline reaching for more than the numbers actually offered. None of that changes what the cosmic web actually is, and none of it needs to. The value of the comparison was never about proving the universe resembles a mind. It was about giving astronomers, and, just as importantly, everyone else, a genuinely useful way to picture something that had never had a good visual reference before now. A cluster of galaxies, a void, a filament stretching for hundreds of millions of light years. These are difficult shapes to hold in the imagination, because nothing in ordinary human experience prepares a person for them. No landscape on Earth, no map of any coastline or mountain range. Nothing built by human hands at any scale a person could ever walk across. A network of branching cells, on the other hand, sitting quietly behind every person's own eyes, is something every listener already carries with them, has always carried with them, without ever needing a telescope to find it. For the first time, astronomers describing the largest structure ever confirmed to exist could point to something the audience already understood intuitively from the inside, rather than asking anyone to imagine a shape with no earthly counterpart at all. A teacher, explaining the cosmic web to a classroom, or a scientist explaining it to a curious neighbor over a fence, finally had a reference everyone in the conversation already shared, one that required no telescope, no simulation, and no specialized training to picture clearly. That kind of accessible reference matters more than it might first appear, because a structure nobody outside the field can properly picture is, in a very real sense, a discovery that stays locked inside astronomy departments, however well confirmed it happens to be. Bring the picture back down to a scale a single mind can actually hold, and the structure stops being abstract entirely. Our galaxy, the Milky Way, sits toward one edge of Laniakea, itself one node among roughly 100,000 galaxies, slowly drifting along shared filaments toward a common gravitational center. Laniakea itself is one region within the larger, unbroken lattice of nodes and filaments and walls that this whole story has been tracing, from Margaret Geller and John Huchra's first thin wedge of sky, through the direct photograph of glowing gas taken decades later. Every star visible from a dark backyard on a clear night belongs to this same structure. So does every star invisible to the naked eye, and every galaxy too faint or too distant for any amateur telescope to resolve. There is no galaxy anywhere in the observable universe that sits outside this pattern, floating free of it, disconnected from the rest. The pattern is not a description of most of the universe. It is a description of all of it, without exception, from the nearest, brightest galaxy in the sky to the faintest smudge any instrument has ever managed to record. Somewhere out, along one of Laniakea's own filaments, close enough to be considered a near neighbor on the scale this story has been describing, other planets almost certainly circle other stars, formed from the very same recycled stardust, built from the very same handful of elements, sitting on the very same web, whether or not anyone there has yet built an instrument capable of confirming it. None of that requires speculation about what such a place might look like. It only requires accepting that the same architecture responsible for building the Milky Way was, by every measurement gathered so far, doing the identical patient work everywhere else this structure reaches. That includes you, sitting wherever you happen to be sitting right now, listening to this in the dark. The calcium in your bones and the iron carried in your blood were not made on Earth. They were forged inside stars that lived, burned through their fuel, and died somewhere along filaments, very much like the one photographed for the first time only recently, scattering those heavier elements outward into the gas that would eventually gather into new stars, new planets, and eventually into you. A star does not simply vanish when it dies. Depending on its size, it sheds its outer layers gently into space over thousands of years, drifting outward as a soft, expanding cloud, or it ends its life in a single violent explosion bright enough, for a few weeks, to outshine every other star in its entire galaxy combined, forging in that brief violence many of the heavier elements no ordinary star could ever produce on its own. Either way, the elements a star spent its life assembling in its core get released back into the surrounding gas, ready to be swept up again by the next generation of stars forming nearby, drawn together along the very same filaments this story has spent so long describing. This has happened many times over, generation after generation of stars living and dying along the same structure, each cycle enriching the surrounding gas a little further with heavier elements. The very first stars in the universe never contained at all. The atoms making up your body did not arrive from nowhere. They traveled here along the same cosmic architecture this entire story has been describing, passed from one generation of stars to the next, node to filament to node again, before ever becoming part of anyone. In the most literal, unpoetic sense available to modern science, you are not simply near the cosmic web. You are made from it, assembled, atom by atom, from material that has been circulating through its structure since long before the sun itself existed. People have looked up and felt small doing it for as long as there have been people to look. Long before anyone had a word for a galaxy, ancient observers tracked the wandering lights across the sky, carved their positions into stone, and built entire calendars and stories around their slow, patient movement, trying to make sense of a sky that offered no explanation for itself, only points of light scattered against darkness, with no visible thread tying any of them together. Shepherds, sailors, farmers deciding when to plant, all of them looked up at essentially the same view available to Harlow Shapley and Heber Curtis before any telescope had settled their argument. A sky of isolated points, each one alone, each one silent. Later generations built observatories, ground lenses, charted eclipses decades in advance, and still the fundamental impression never changed very much. Points of light, scattered, each one separate from the rest, with darkness filling everything in between that no instrument seemed able to explain away. The feeling that produced a mixture of wonder and a kind of quiet loneliness shows up again and again across human history, in old poems, in old prayers, in the simple, private thought almost everyone has had at least once, standing outside on a clear night, of how very far away everything actually is, and how very small a single person standing on a single planet must be by comparison. That feeling was never foolish. It was an entirely reasonable response to the only evidence available at the time, one point of light at a time, with nothing yet able to show what, if anything, connected them. Even the scientists at the center of this very story felt it. Geller and Huchra spent their careers surrounded by that same silence, measuring one galaxy's distance at a time into the small hours of the morning on a cold Arizona mountaintop, with no guarantee that a recognizable pattern would ever emerge from the work at all. Think back to that first image this story opened with, a single farmhouse window glowing alone on a dark road at midnight, with no other light visible for miles in any direction. That image was never inaccurate. Exactly. From where you might be standing on that road, in that darkness, the next lit window really would be too far away to see. The feeling of isolation it produces is honest, understandable, and, for most of human history, unavoidable, since the only evidence anyone had access to was whatever the unaided eye could gather from one particular spot on one particular night. But an image built entirely from what is visible from a single point in the dark is not the same thing as an accurate map of what actually exists. The other houses along that road do not stop existing simply because their lights cannot be seen from where you happen to be standing. They are there, whether or not their light reaches you, connected to the same road, drawing from the same power line, part of the same township, whether the darkness between them ever gets acknowledged or not. Wait for daylight, or climb whatever hill happens to be nearby, and the same road that looked so empty at midnight reveals itself to be lined with houses the whole way, each one exactly where it always was, never actually isolated, only ever unseen from that one particular vantage point in that one particular dark. That has always been the real story of the cosmic web, and perhaps of every important discovery that ever forced human beings to reconsider how alone they actually were. People have looked up at the night sky for as long as there have been people to look, and it is a profoundly natural thing to feel small doing it, even a little abandoned, one point of light among countless others, each one impossibly far from every other, with nothing but cold darkness stretching between them. That feeling is not a mistake, and nothing in this story is meant to talk anyone out of having felt it. It is a completely reasonable response to what the unaided eye, and even most telescopes built across most of human history, were actually capable of showing anyone. But feeling alone and being alone are not the same claim, and only one of them turned out to survive contact with better instruments. Every galaxy human beings have ever photographed, mapped, or measured sits somewhere along one continuous structure of gravity and gas, tied to every other galaxy by filaments that took decades to prove were real and, in the end, only a few years to finally see with our own instruments. The separation was never in the universe. It was only ever in how much of the universe, any single vantage point, including the one every person is born into, has ever been able to take in a single glance. Margaret Geller spent a career proving exactly this, one patiently measured galaxy at a time, decades before anyone had a photograph to show for it. And every survey and every image described in this story since has only confirmed what her own thin wedge of sky first suggested back, when the idea still struck most of her colleagues as unlikely. This is not a small correction, even though it changes nothing about how any of us actually live. Nobody's rent changes. Nobody's health improves. The world tomorrow morning will look exactly as it would have looked, regardless of whether the cosmic web had ever been photographed at all. But something quieter shifts, all the same, in how the whole picture fits together. For as long as human beings have had the capacity to wonder about their place in the universe, the two available answers have tended to be a comforting story with no evidence behind it, or an honest accounting of the evidence that left most people feeling smaller and more alone the more carefully they looked. This is neither of those. It does not ask anyone to believe the universe was built with a purpose, or that any of this was arranged for anyone's benefit. It simply reports what the instruments, after decades of patient work, finally managed to confirm: that the appearance of separation, however convincing it has always felt from the ground, was a limitation of the viewpoint, not a fact about the territory. Two honest positions used to be available to anyone thinking carefully about their place in the universe, comforted by a story the evidence never supported, or genuinely informed but left with a picture that made the darkness feel wider than it turned out to be. A third position is available now, quieter than either of the old two, asking for nothing to be taken on faith and nothing to be mourned, only for the actual shape of the evidence to be allowed to stand as it is. Nothing about that discovery makes the universe warmer or friendlier or built with anyone in mind. The filaments do not know they are connected to anything. The gas does not care what it feeds. Gravity was doing exactly what gravity always does, long before there was anyone around to notice, and it will keep doing the same patient work long after everyone listening tonight. And everyone who ever built a telescope has been gone for longer than any of the stars discussed in this story have existed. There is no design in it, and no message waiting to be decoded, and nothing in the evidence gathered so far asks anyone to believe otherwise. It would be easy, at the end of a story like this one, to reach for something grander, to promise that the discovery means the universe cares, or watches, or was somehow waiting for someone to notice its shape. It was not. The filaments formed the same way whether or not anyone would ever build a telescope capable of finding them, and they will keep existing in exactly the same shape long after every telescope built so far has gone silent. A structure this patient does not require an audience to keep being true. It simply is, whether observed or not, exactly the way it was before the first person ever looked up and wondered what held it all together. What the evidence does show, plainly and without needing any embellishment, is that the old picture, countless separate islands adrift in featureless black, scattered at random, with nothing truly connecting them, was simply wrong. Not wrong because it was foolish to believe, wrong because nobody yet had the instruments to see any farther than one porch light in the dark. The instruments exist now, built patiently across a full century of careful work, from a thin wedge of sky measured one galaxy at a time to a single photograph of gas that took hundreds of patient hours to finally develop. And what they show, however quietly, however far short it falls of any grander meaning, is that every one of those lights was on the same road all along, joined by the same gravity, built from the same handful of elements, threaded together by filaments that took the better part of a century to prove were real and, in the end, only a few short years to finally see with our own eyes. That is the whole of it. Not a message, not a plan. Only the plain, patient, thoroughly confirmed fact that nothing out there was ever quite as alone as it first appeared, including on a night dark enough to see it clearly. You sleep well. The web that holds the galaxies is holding you too.